Now we're on to question 9, about pennies and taking all the charges, or at least one charge from each atom, away from penny. And we're finding basically that there's a lot of charge in normal matter. So here we're saying, just some fun facts, trivia about US pennies, that they're 2.5 grams and they're 2.5% copper. So now we want to find out the mass of 1 mole of copper. It tells you this, so we don't have to worry about it. How many atoms of copper in this penny? This is basically a chemistry question, but it's giving you all the information that you need to figure it out, with the exception of some constants, which you can get in your formula sheet.
So what we're told is 2.5 grams, 2.5% copper. So mass 2.5 grams times 2.5%, that's 2.5 over 100, so I don't make any mistakes. That's 6.25 times 10 to the minus 2 grams of copper. Now we want to find out how many atoms of copper this is. We're told that a mass of 1 mole is 63.546 grams, so we have a mole of copper, because that's what we're trying to find. And we're going to divide by how many grams? That's 63.546. So grams of copper are going to cancel, and we're going to be left with moles of copper. In terms of the numbers, we have 6.25 divided by 63.546 times 10 to the minus 2, and we're going to have moles of copper in the end. Gives us 9.83 times 10 to the minus 4 moles. Do we care? Not really. That's not what we're trying to find. We're trying to find out how many atoms of copper this is. We have Avogadro's number, and that tells us how many atoms per mole. We know how many atoms we have, and so if we're going to remove 1 electron from each copper atom, how many total coulombs would this be? So we've got a number of atoms that's equal to the number of electrons that we're talking about. And so we just need to multiply the number of electrons by the charge of 1 electron, which is the elementary charge, which we can get off of the formula sheet. 5.921 times 10 to the 20th electrons, because that's how many copper atoms we had. We're taking 1 from each. And then we're saying the charge of an electron, so we're going to multiply this by the charge. And that's 1.6 times 10 to the minus 19th coulombs, and that's per electron. We get 94.73 coulombs of charge, which is a lot, and it's going to be negative for the electrons. We've got the electrons at one end of the Earth, the remaining copper ions at the other end of the Earth. So we have a distance of 1.271 meters. I didn't make you do any conversions there. I gave you the number. So here we just use Coulomb's law. We are looking for the force between them. That's Coulomb's law. That's K, Coulomb's constant, Q1, Q2 over R squared, the distance. Q1 and Q2, the charge of our electrons. K, we can get from the formula sheet, which in the formula sheet is 9 times 10 to the 9th. What are the units? Newton meters squared per coulomb squared. And now we're going to have this 94.73 coulombs squared, but coulomb squared and coulomb squared in the denominator are going to cancel out. That's pretty nice. So that works. And then we have the distance, r squared, but that was given to us. That's 1.271 times 10 to the 7th meters. And we square that whole thing. And the meters squared are going to cancel out here. So all that we're going to be left with is newtons. And that's pretty great. In terms of our numbers, 9 times 94.73 squared divided by 1.271 squared. And then we're going to have 10 to the 9th minus 14, right? Because we've got 10 to the 7th down here, and we have that twice. And then in terms of our units, we're just left with newtons. And I get almost 5 exactly. So 4.99995 times 10 to the minus 1 newtons. Now this next question doesn't follow on from the previous questions except for the amount of charge that we've got. So here it's saying that if we had all this copper and it didn't expand when we removed all the electrons, which of course it would because the copper ions would repel each other terrifically, but we're ignoring that. So we're saying that it's going to stay in its little bead of copper, and it's going to have a radius of about 1 millimeter. And we want to know the electric potential at the surface. This is just a matter of using the formula that's in the formula sheet and that we derived from integrating Coulomb's law. And that formula is just basically looks like Coulomb's law, except that the denominator has just the radius to the first power instead of the radius to the second power. V is just going to be kq divided by r. So in that case, that's 9 times 10 to the 9th Newton meters squared per Coulomb squared. Times Q is 94.73, I think. And R is our now 1.19 times 10 to the minus 3 meters. And that gives us a large number, 7.16 times 10 to the 14. What are the units? Well, we have Newton meters, because only 1 meter canceled out, so we have Newton meters, and only 1 Coulomb canceled out. That's coulombs. But look at this, Newton meters, that's joules, joules per Coulomb, so that's 7.16 times 10 to the 14th volts. That's a pretty high voltage. Remember 6 is mega, 10 to the 9th, that would be giga, 10 to the 12th would be tera, so this is 700 teravolts. Suffice to say that it's not going to be possible to keep this blob of copper together. It would blow up. Next, question E follows right on from this. If the electrons were initially only that far apart from the copper, so we have the electrons, so we just, are pulling them apart, how much work does it take to take them to infinite separation? So the work is just going to be the voltage times the charge, so that's going to be another Q here. So basically you'd have to multiply this number by 94.73 coulombs again, because remember the voltage is the work per charge. So that's going to be 7.16 times 10 to the 14th volts times 94.73 coulombs. And that's going to be 6.79 times 10 to the 16th joules. This is a heck of a lot of joules.